In this video, we are going to discuss about dual slope ADC. So in the previous class, we have discussed about single slope ADC. So in the single slope means you have um, only one slope, right? Like this. Okay. So this is a slope. Here you can see I have a integrator and comparator and AND gate and up counter. This is similar to that of single slope ADC. In addition to that, I have a overflow bit. So if it is 0, V in gets selected. Okay, if the overflow bit is 0, if it is 0, this becomes V in. Or if it is 1 means this will be selected. So you will get minus VREF. Okay. So initially I take the overflow bit is equal to 0. Overflow bit is equal to 0. So V in gets selected. So the V in is the input for this one. So it will integrate. So I will get V in is nothing but my analog signal. So and what is Vx I will get? Vx is equal to integration of this Va. So let me take 0 to t. Okay. Va of dt. So minus, this is minus, right? So minus of minus 1 divided by RC Va into t. So for this one, if I draw the diagram, the slope will look like this, right? So this is a time. So if I take this is t1, okay. So this is a t1 time. So till this one, I have the slope. The value of the slope is nothing but so this is my Vx, right? So that is equal to minus 1 divided by RC into Va into Va. So this is my time. Okay. So up to how much value it will count? So it will, the t1 value is equal to 2 power n of t clock. Okay, so why I am taking t1 is equal to 2 power n of t clock means so this, if it is suppose it it is a 2-bit counter means it will count from 0001. So it will count from 0001, 10 and 11. So once if it reaches 00, so the overflow bit becomes 1. Okay, so till this one it is taking 2 power n t clock. Okay, that is it is taking 4 t clock speed. It's 1, 2, 3, 4. Okay, so I can write this one as so I have taken Vx is equal to VARC into T1. So the T1 value is nothing but this is minus 1, right? So minus of VA, the RC, 2n of T clock. So I can take like this, right? So the slope also it will look like this. The T1 value is thing but 2 power n T clock, and the T1 value is fixed. Okay, so always fix whatever the value of V is. Okay, so this is nothing but your VXL. Okay, so once if this is happen, so my input get changed. So the input is nothing but suppose if the overflow bit is 1 means the input to the integrator is minus V reference. So if the input to the integrator is minus V reference means Vx is nothing but Vx of t. Vx of t is nothing but minus 1 divided by RC into integration of so from t1 it will go to t minus V reference of dt plus my initial voltage. So the initial voltage is nothing but VA divided by RC into, that is minus VAD, minus VA divided by RC into T1, right? So you can see initially this is my slope, right? So this is nothing but VA divided by RC minus VA divided by RC. Okay, and this value is nothing but my Vx, right? So this is my time. So from T1 it will go to, so till this one it will go, right? So it will not change, it will not go more than this 0, right? If it is goes 0 means the comparator will get changed, right? So it will go not beyond this 0 value. And you can see now this I am taking it as T1 2. So this time is nothing but your T1, and this value is nothing but T. Okay. So if I solve, I will get so if I take V reference common, I will get T minus T1 minus VA divided by RC into T1. So we know that the T1 is nothing but 2 power n T clock, right? So if Vx of t is equal to 0, so at this point Vx of t is equal to 0, so 0 is equal to V reference by RC T minus T1 minus VA divided by RC T1. So V reference divided by RC into T minus T1 divided by VA divided by RC into T1. So these two get solved. So I can write my VA is equal to V reference divided by T1 into T minus T1. This T minus T1 I am writing it as, this is my T1, right? So T minus T1 I can write it as M. And we know that T minus T1 is nothing but N, and T1 I can write it as 2N T clock pulse, right? It's proportional to my input signal VA. So if VA get changes, okay, so for this VA I'm getting this slope. So suppose the VA value is more means I will get like this. So the time period get increased, okay. So if VA value is very less means again the time period get decreased. So this time period depends upon the value of my input signal. Okay. So let us solve one problem based on this. But you can see that T1 value is always fixed for whatever the value of the input signal. So first the question is for dual slope ADC, it is a 16-bit counter. They are given it is a 16-bit counter and a 4 MHz clock rate. Maximum input voltage. The maximum input voltage is 10 volt. That is my EA. Okay. The maximum integrator output voltage, that is Vx is minus 8 volt when the counter has cycled through 2n count, right? So the capacitance value of the integrator they are given as 0.1 microfarad. So what is the value of the integrator? So this is what they are asking. So you substitute this first formula, you take this first formula. So Vx is equal to minus Va Rc into 2 power n t clock. So this is a formula. So the Va they are given as 10 volt. Okay. 10 volt, and they have asked to find the R value. C value 0.1 microfarad and Vx value is minus 8 volt, and it is a 16-bit value, so 2 power 16 into t clock. So they have given it as clock rate. So it is in terms of frequency, so I can substitute 1 divided by 4 megahertz. So once if you solve, you will get the answer as 205 kilo ohm. Suppose if they are given the time, the analog signal value, okay. So the analog signal value is, if the analog signal value is 4.129, find the equivalent digital value, digital number. So this is what the question. You can substitute in this formula 4.129, that is equal to V reference is 8 volt divided by 2n t clock pulse. So this is taking n into t clock pulse. Okay. So if I solve, I'll get V reference n divided by 2 power n. So small a. Okay. Suppose if the question is given Va is equal to plus or minus 4.129 volt of means I can write 4.129 equal to 8 divided by 8 divided by 2 power n clock pulse. 2 power n clock pulse is something that 65536 into n. Right. So I can write n is equal to 65536 into 4.129 divided by 8 volt. That is equal to 33825. So the equivalent value of this binary bit is this number is 140140140